Hey, it's Mr. Saltana. This video is going to be on radioactive decay and nuclear equations. So first, just a reminder that they're called nuclear reactions because they have everything to do with the nucleus, right? So electrons are no longer part of the equation here. We're just focusing on the nucleus, just the neutrons and the protons. And also a reminder that the protons are the element's identity. So for example, if I put a neutron here, that doesn't really mean anything to the simulation. But if instead I put a proton here, now the simulation knows, okay, that's hydrogen. So an element's identity is specifically because of its proton number. Now, right now it says stable. If I keep adding protons, even after the first proton, the nucleus has already become unstable. Now, if I were to keep going, it would just become more unstable. But if I add neutrons, that actually stabilizes the nucleus. So we start to realize right away that what makes an unstable nucleus is the ratio of protons to neutrons. If you don't have the correct ratio to sort of match each other to a certain extent, then what happens is the nucleus is unstable, which does make sense, right? Because those protons are all positive, so to some extent they're all repelling each other because they're all the same charge. Just like opposites attract, the same charges are going to repel. So we have this unstable nucleus. What does this all mean? An unstable nucleus is a radioactive element. That's where that comes from. So those are the dangerous ones that are emitting radiation, essentially. The reason why they emit radiation is because they're trying to stabilize again. They're trying to get back to that stable nucleus, and then so they'll get rid of particles in order to get there, in order to get back to a stable nucleus. So see how I removed a proton, for example, and this stabilized? Something similar is going to be happening with these atoms, but that's what makes something radioactive is it's got unstable nuclei and it's firing out particles to try to stabilize. What it's firing out is the dangerous thing that causes cancer and things like that, and does damage to people's organs and things like that. So that's kind of what we're talking about, is the different types of radiation that can happen as the result of an unstable nucleus. So here what we're looking at is called the band of stability. And there's kind of a lot going on in this graphic, but we just want to know that the x-axis are the number of protons. So as we go to the right, the proton number is going up in the axis. And the y-axis is the number of neutrons. So as we're going up, the neutron number is going up. So sort of that sweet spot where we want to be is called the band of stability. And that's a certain ratio of neutrons to protons, just like we saw. So if that ratio of neutrons to protons is 1.5, that's sort of the higher range. So we're still okay there, and we can be anywhere from there to a ratio of neutron to protons of 1. So in other words, if we had equal numbers of neutrons and protons. So if we fall within that range, usually we're okay, and the nucleus is stable. It's when we get out of that range that this nuclear decay is what it's called starts happening, where elements are radioactive and they begin to fire off particles to try to stabilize again. So the first type of radiation we're looking at is called alpha radiation, or in other words, alpha particles. And so here's our original nucleus, and we can see that it has fired off an alpha particle. What makes something an alpha particle every single time, don't forget this, is that an alpha particle always has 2 protons and 2 neutrons. No matter what, that's what makes it alpha radiation. So every single time you got alpha, 2 protons, 2 neutrons. In fact, because it has 2 protons, we consider it the same thing as a helium nucleus, because helium also has 2 protons. It's number 2 on the periodic table. So what we're saying is this was originally a larger nucleus that used to have that particle as part of it. It fired off that helium nucleus, and now this element has changed because it dropped 2 protons. Let's see in more detail what that looks like. Here it is. So we started with uranium-238. Remember that the top number is the total number of particles in the nucleus. So if we were to count all these up, that would give you 238. And the bottom number is just the proton number in this notation. So in other words, uranium has 92 protons. That's what makes it uranium, right? Okay, but this uranium-238, is unstable. It's not a happy nucleus. So it's undergoing decay. It's radioactive. And it's releasing this alpha particle as a result, this helium nucleus. So helium nucleus is always going to be 4/2, right? It's got 4 particles total in the nucleus, and 2 of those are protons. That's what makes it helium. And what's left over afterwards is this thorium. So that's what we're seeing, is that we see this larger nucleus, it emits an alpha particle, and what's left over is thorium. So this is going to be the case for all of this nuclear decay, where you're going to start with a larger unstable nucleus, and it's going to break apart into two relatively smaller nuclei that add up to that original nucleus. So notice that 4 plus 234 gives you 238, right? This arrow is like an equal sign, and 2 plus 90 gives you 92. So that's how it works when we're trying to actually balance these nuclear equations. It's a little bit different because we made brand new elements, because we had a certain number of protons here, and then the proton number split into 90 and 2, so whole different elements. But the goal will still be the same, of trying to make the top numbers, trying to make the numbers equal on both sides. In this case, we're trying to make the top numbers equal and the bottom numbers equal. Yeah, so that's alpha. Alpha always has a helium nucleus coming off. And in alpha decay, the mass number and atomic number both change. So we went from a 238 and a 92 to a 4 and a 2 and a 234 and a 90. So really going from here to here, both numbers changed. Also, alpha particles probably sound familiar, right? Remember, that's what Rutherford was using in his gold foil experiment. So what's contained in this lead shield is actually some radioactive material. And it's firing off alpha particles because it's undergoing radioactive decay, essentially. It's trying to stabilize the nuclei of the radioactive element that's in there. Okay, the next type is beta radiation. So this one's a little bit more complicated and really interesting. We again begin with a nucleus that is unstable, right? Nucleus is unstable. But the odd thing that happens here is something you've probably never heard before. In beta radiation, you take a neutron from the nucleus, so one of our blue particles, and it actually converts into a proton and into an electron. Now, the proton stays behind as part of the original nucleus, but the electron gets fired away, and that's what we're looking at here. So normally we consider electrons as being outside the nucleus, right? But what we're saying is a neutron from in the nucleus can convert itself into a proton and an electron. It's like crazy stuff. Here is that happening. So if we look really carefully, starting off with thorium-234, and here's an odd thing that happens. So notice how first it's got this white one is considered a neutron originally, but it converts itself into a proton. It turns blue, and while it does that, it releases an electron, which is what we call a beta particle. Beta particle is really, for all intents and purposes, an electron. And same thing over here, we're balancing the equation. So we got 234 arrow, 234 plus 0, and then 90 equals 91 plus -1. So this is the part that everyone messes up, so you want to pay extra close attention to this one. A -1 plus a 91 is actually going to give you 90 over here. Or a 90 equals 91 plus -1. Both ways of looking at it. So in this case, we actually only had the bottom number, the atomic number, change. So that's something kind of unique to beta decay. We see that here as well. Here we have carbon-14, which we'll talk about later, is converting to nitrogen. So it's weird. It's lost an electron, but the bottom number went up. Notice, because one of the neutrons that was in the total converted itself into a proton. So now the total at the top is still the same because the top is protons plus neutrons, but now the bottom number, which was just protons, has gone up. So it's kind of weird that way. We released an electron, and yet our numbers went up on the bottom because now we have one more proton. It used to be a blue neutron, now it's a green proton. Last type is gamma radiation. So this type, very high energy. It's really just a high energy wave, and it usually, as a result, it comes out with the rest of the nuclear decay. It's not like its own separate thing. It'll come out with the other ones. So for example, here's an alpha decay, and then gamma was just part of that result as well. Gamma should sound familiar too, right? That was part of the electromagnetic spectrum. Those were the most penetrating, most dangerous rays on here, were the gamma. Okay, very last thing is that these different types of radiation have different properties to them, right? Because they're different things. So let's say this radioactive source is giving out all three types of radiation. The beta radiation would go through the slit and be attracted to the positive plate, because remember, beta particles are essentially just electrons, so the negative is attracted to the positive and it gets deflected upward. The alpha particles, when they come through, are actually repelled by the positive because of the same charge as them and attracted to the negative. So then that actually goes downward. So remember that a helium nucleus is what an alpha particle is. So we're talking 2 protons and also 2 neutrons. There's no electrons there, so if you just have 2 protons, that's giving you a positive charge. So alpha particles are positive. You may remember that from the gold foil experiment too, because they were repelled by the nucleus of the gold atom, right? Because the nucleus was positive and the alpha particles were also positive. Now the gamma particles shoot straight through the middle, and that's because they have no charge. They're not attracted to the positive plate or the negative plate. Another thing we want to be aware of is that how penetrating are these? Alpha particles are the least penetrating. They get stopped by paper. Beta particles can penetrate paper, but they'll be stopped by aluminum. And gamma particles gamma rays, I should say, are the most penetrating. They'll pass right through most things except for lead and concrete. It's sort of like Superman's X-ray vision, gamma, and that's because they're very close to X-ray on the electromagnetic spectrum, right? It's right next to it. So gamma is the most penetrating, the most dangerous. It can pass through the most things. Okay, so this table, if you want to pause, we're going to need to know this table by the end. We want to know the relative charges, what particle it is, description of the radiation, as well as like how penetrating it is. So alpha particles are the same as helium nuclei, so they have a 2+ charge because of those 2 protons. Beta particles are the same as electrons, so they have a 1- charge. And gamma are really high energy photons, so they have no charge. And then this is what they can go through. You don't have to worry so much about the approximate energy. So that's it for radioactive decay and balancing radioactive equations. Thanks for watching. Remember, chemistry is everywhere.